Good morning, Max. How are you?
I'm tired and somewhat confused. This puzzle kept me up all night, and I'm not sure IP will be any good for it.
Let's see if I can help.
Okay, it is a puzzle from plastilina.net called The Lonely Night. Lonely and depressing, I would add.
But you are not lonely solving it anymore. You've got me in integer programming to help you out.
I already thought of integer programming, didn't work out. You are my last hope.
Alrighty, the problem solving starts with a detailed analysis of what is given. Let's read the rules carefully.
The rules are easy, it's the solution that is hard to get. I feel like I'm playing a lottery here, the chances of winning are about as high.
Explain it to me.
Okay, to go from the green castle to the blue castle, the knight needs to visit each of the 14 squares once and return to where he started. The knight step must be like a knight move in chess.
Does it matter which square you start with?
No, you can start anywhere you wish. I probably tried all the possibilities already. I like the fact that the squares I can go to next are highlighted, makes it easy for people who don't play chess, but this crow is really annoying, makes this thing even more depressing. See, no matter how I try, the outcome is always the same. Optima, are you still with me?
Sorry, I'm thinking. Okay, looks like we are dealing with an instance of the famous traveling salesman problem here. It is a notoriously hard combinatorial optimization problem.
I think I've heard about the traveling salesman problem before, but I can't recall what it is about.
No worries, I'll remind you. In the traveling salesman problem, TSP for short, we are given a set of n cities and a matrix of pairwise distances between them. The salesman's tour is supposed to start and end at the same city and should include one stop in each of the remaining cities. The objective is to minimize the total distance traveled.
I see, we can think of our squares as cities, then we need to find a tour covering all the squares. But what would be the pairwise distances and what do we need to minimize? We just need one tour, that's all, but I couldn't find any in several hours I spent trying. In the TSP we are supposed to be able to travel between any pair of cities, and here our possibilities are limited. There are very few squares we can go to next.
You are actually right, TSP may not be the best model to use in this case. I have a better idea. We can represent our problem data as a network in which the nodes correspond to the squares. We will connect two nodes by an edge if we can move between the corresponding squares.
Then our problem reduces to finding a tour passing through all the nodes, right?
Precisely. This problem is called the Hamiltonian Cycle problem. It is still hard.
Tell me about it.
But you know what? We can formulate it as an IP and the solver will do the rest.
Okay, how about introducing a binary decision variable for each edge in our network? If the edge ij will be used in our tour, then xij is 1, otherwise it is 0.
Sounds good to me.
And what about the objective? We don't really need to optimize anything, we just need to find a feasible tour.
This is correct. But I suggest we pick some arbitrary objective function anyway.
I like maximum better than minimum for sure. I suggest we maximize the sum of all the variables.
Works for me. How about the constraints? We need to visit every node exactly once.
The salesman needs to enter each city and to leave it, and he needs two edges in the corresponding node for that, one to enter and the other one to exit. So, for every node either summation of xij's such that j is adjacent to I must be equal to 2, right?
This is correct. We call these the degree constraints, because they essentially say that the degree of every node in our solution must be equal to 2. We are making a good progress, but we are not done yet.
I know, that would be too good to be true. Clearly, the constraints we have don't guarantee that the solution will yield a single tour.
Yes, it's possible that we will get a bunch of subtours, as in this example. Even though every node has the degree of 2, this doesn't solve our puzzle.
We need to eliminate the possibility of these subtours somehow.
Yes, And this leads us to the subtour elimination constraints. But first let's introduce a notation we'll need. For a subset S of nodes, let E of S denote the set of those edges that have both endpoints in S.
Then to eliminate a subtour creating a cycle on the nodes from S, we need to make sure that the number of edges from E of S that are included in the solution is less than the number of nodes in S, right?
Yes, but we only need to require this for S that contains at least 3 nodes but not all the 14 nodes.
Indeed, a subtour with less than 3 nodes is impossible, and a subtour of 14 nodes would be exactly the tour we are looking for. We certainly wouldn't want to eliminate it.
Let's illustrate the subtour elimination constraints by observing that they would not be satisfied by a solution shown in our figure.
So, if we added the subtour elimination constraints to our model, there is no way we would obtain a bunch of cycles. We can only get the one containing all the nodes.
That's right. So the model we have now is complete.
This is lovely, but how are we going to feed all these subtour elimination constraints to the solver? Just thinking about enumerating all the possibilities for these subsets S makes me sick.
You are very good at recognizing the challenges, Max. But I have a good news for you. We will use a lazy approach to generating these inequalities.
Lazy sounds promising, but would you mind clarifying what you mean?
Sure. We will ignore these constraints and will only add them whenever they are not satisfied by a solution we obtain. Dropping some constraints enlarges the feasible set, leading to what we call a relaxed problem.
Lazy and relaxed. I surely like this.
I knew you would appreciate this terminology, but don't be fooled by it. The relaxed problem may be easier to solve than the original one, but this comes with a price. The solution we obtain may not be feasible for the original problem.
What do we do if it is not feasible?
We identify violated constraints among those that we dropped from the original problem and add them to the model.
Are the violated constraints easy to identify?
They are not in general, but should be easy for a toy problem like ours.
Toy problem. This toy kept me up all night.
Anyway, we got the model now, let's implement it.
Will we use ample?
Yes, ample is fine. We need to decide on the data structure. The input network could be stored in several different ways in our data file.
My favorite data structure for a network is the adjacency matrix. It has as many rows and columns as there are nodes, and whenever there is an edge ij we put 1 in the positions ij and ji in the matrix. We fill the rest of the matrix entries with zeros, but I was too lazy to do that, so I just left them blank.
Great effort, Max, but I don't think we will use adjacency matrix. There are only 20 edges in this network. You don't want to use 196 numbers to store it. We will be better off just listing all the edges.
Okay, I agree, I like this lazy mentality.
I prefer to use the word efficient.
You know what Bill Gates said? I choose a lazy person to do a hard job because a lazy person will find an easy way to do it.
And what's your point?
I wish I were that sort of lazy.
Be careful what you wish for. I am not sure you would enjoy doing a hard job for Bill Gates. Okay, here come the ample model and run files.
So, we have the set of nodes n and the set of edges e, which is a subset of the set of ordered pairs of nodes. We have a binary variables xij for each edge ij. The objective is to maximize the sum of all the variables. Now, the degree constraint looks massive for some reason.
Yes, since the set E was defined over ordered pairs of nodes, the pair ij is not the same as ji. To make sure that we count all the neighbors j of I, we use 2 sums, one over the pairs ij, and the other one over the pairs ji.
Makes sense.
Okay, let's solve it. If we are lucky, we could have a solution to the puzzle within a few seconds.
Fingers crossed. Oh no. We got 2 subtours. Bloody solver.
Don't blame the solver for your model. Just 2 subtours while ignoring all the subtour elimination constraints is actually not too bad.
I can't wait to add that lazy cut.
Go for it.
Here it is. As a true admirer of all things lazy, I picked the smaller of the 2 subtours to generate the cut. My intuition tells me that this should suffice.
Your intuition is correct, in fact. If you also added the inequality for the larger subtour, it would have been redundant anyway.
Okay, let's run it. Yes, we got it. We solved the puzzle. Hooray!
Of course we did, silly. What would we be good for if we were unable to solve this one?
Optima, can't you be happy for once?
Maybe I would be happier if we built a better model. If you would show our solution approach to IP experts, they would laugh.
Why so?
Well, this model is not very tight, and the way we added the lazy cut was very amateurish. But it would take me a few lectures to explain precisely what I mean.
I think we are off to a great start. Even this model got the job done for us.
As long as you are happy, Max.
You know what would make me really happy right now? To actually see our noble knight crossing the bridge.
Ha ha. Make sure you record the solution and convert it into the actual knight moves.
Done. Isn't this the most beautiful key to a puzzle you have ever seen?
Maybe. You've done a terrific job with it. Maybe you should have majored in art.
LOL. I appreciate the encouragement. Now let's go and test the reaction of that bloody crow to the knight crossing the bridge. I've been waiting for this moment forever.
Just do it already.